Welcome to my video on dark matter and dark energy. Well, what you just saw is a stinger made by my son David. I don't do those kinds of things, but I want to personally thank him for doing that for me. And he's done that for other YouTubers who are part of the dissident science group. And so today we're talking about dark matter and dark energy. And if you're new to the particle model, please review and watch the particle model overview and levels of the universe. Gives you good basics about the particle model. I can't always explain everything in each video. And then I try to highlight another video that happened to get a good response, and EM radiation was one of those. So if you're new, stop, maybe look at these, and then come back and you'll understand better what I'm talking about. My last video was about a list that I found on the internet of 5 great problems of physics. And I'm going to go over one of them today. It's number 5, the problem of cosmological mysteries. And those mysteries focus around dark matter and dark energy. Well, it turns out I've done one on dark matter, and so I'm going to just do a general review, but here again are some videos that I've done. The first one is a video that I've done as your particle model guru, titled Dark Matter versus G. And I also did a similar one, very similar to that at the CPNS conference. It's also on the internet, and there's the link to it. So that'll give you a more complete description, but I will go over it briefly to highlight the points being made. And this is one of the main points. We have a chart here of the velocity of the stars at the edge of the galaxy. Well, actually, it's the velocity of the stars not only at the edge, but down by the center of the core. And the blue line is the measured velocity, and the red line is the calculated value. And the problem is the measured value is much higher than the calculated value, and that's not good. Something's wrong, something's amiss. So scientists look at that. And this is an equation. I don't often use equations, but I try to keep it simple. You can find this on the internet, where the velocity of an object in a circular orbit, by the way, this is specifically circular orbit, is equal to the square root of Newton's gravitational constant, the mass of the object that the star is circulating. And that mass is all at the center of the, in this case, the galaxy. And r is the distance of the star from the star to the center of the galaxy. When physics use this equation to calculate, they get this value which is too low. Well, here's the particles model answer. Well, let me back up for a moment. Let me explain why I almost missed the point. So they look at this equation and they say, okay, in order to make the velocity higher, I must make g higher, m higher, or r smaller. Well, you look at g, and that's Newton's constant, and you're not going to change that. I mean, if mainstream is locked into anything, if they're locked into their constants, they love their constants, and they're not going to change. Distance. You might remeasure the distance of the particular star you're looking at and get a different answer, but to explain that large a gap would mean a large change in r. So the only thing left is mass, and what can you do about mass? You can increase the mass, and you can make it work. Oh, there must be matter out there that we don't know about, that we can't see, that the stars know gravitationally, but we don't know. They call it dark matter. They need it to get the red curve to match the blue curve. Well, the particle model's answer is that the G1 gravity is in fact the equivalent of Newtonian gravity. And what you have in G1 gravity is you got G1 particles coming at the galaxy from all directions. And a little drawing I made here is looking at the side of the galaxy. And this is the galactic plane. And the G1 particles that happen to come this way, and there's G1 particles passing through this way, and most of them pass through, but some of them either hit or scatter or get trapped. But by the time these get over to here, this arrow is smaller, showing that there's fewer particles. So you have a larger number of particles at the edge, which I claim helps explain it. Which means, in effect, it's G that changes. I'm not changing R. I'm not changing the mass. I'm changing G. Yes, the gravitational constant changes throughout the galaxy. And one of the ways to show this, to re-explain this, is if I look at this is the center of the core again, and there's the core, there's the open space, there's the first arm, there's open space, and there's the second arm in open space. I didn't do the whole drawing. But here again, you have the number of particles coming in, and as they go through open space, well, maybe there's something there. It loses a few particles, but when it goes to the arm, it loses a lot. Then open space, it loses a little. Then when it goes to the core, it really loses it. And it arrives here, it has fewer particles. This is smaller than this. This line is an extension of one from the other end, and the assumption is that they both arrive at the center approximately the same number of loss. Well, so this length and this length are the same, and this loses and loses until you get this differential, and that's that differential. What is interesting to note that I didn't mention, I'm going to go back to the graph, is that this blue curve, you can actually see our galaxy in this blue curve. It's quite amazing. This is the velocity at the center of the core. This is the edge of the core. This is the first gap. This is the first arm of it. There's the second gap. There's the second arm, and so on. Amazing. You can actually see it. Now, there's different curves that don't show it exactly that way. I did pick this one because it shows it clearly, but I claim that it's quite amazing to see the distribution of the mass within the galaxy just by looking at the velocity curve. And so we move on to dark energy. Okay, so as I normally do, I look up dark energy, and I use Wikipedia a lot. You can verify that that's what I did, and that's what I'm quoting is correct. And sometimes I agree with it, sometimes I don't. But I do when I quote it, I quote it literally. Dark energy in physical cosmology and astronomy is an unknown form of energy. So they invented a form of energy, and they don't know what it is. This is physical cosmology, and they're just going to say, yeah, I got a bunch of energy. And it's hypothesized to permeate all of space, tending to accelerate the expansion of the universe because those velocities at the size of the universe, in this case, it's the size of the universe that's growing and growing faster. You know, if you have a Big Bang, if you had a Big Bang, after the Big Bang, everything's moving at a given velocity. If you want it to, if it needs to, or is seen to accelerate, you have to have a force. You have to have something pushing it. But here, the forces they call energy. Dark energy is the most accepted hypothesis to explain the observation since the 1990s, indicating that the universe is expanding at an accelerating rate. Particle model would insist that you tell me what's behind this energy, what kind of moving obstacles, particles are happening to push the galaxy apart. So how much dark energy do you need? Well, you got a neat little graph also from Wikipedia, and this is 4.9% of ordinary matter. That's what you see, you know about somehow. And in order to explain the curve at the velocity at the edge of the galaxy, you need dark matter. We just went through that briefly. And according to their estimate, if you have 20%, 26.8% of all the matter and energy around the galaxy, that would help bring the velocity of the stars up to where the measured values are. So you need this dark energy to adjust the velocity, and then you need this, that's dark matter, excuse me, and then you need dark energy to explain the accelerating. 68%. There's a lot to overcome the forces here that are pushing it together versus the ones that might be pushing it apart. Is the universe expanding? Well, I have another video that I've done called Redshift and Tired Light. Depending on your assumptions, you can conclude that it is expanding. If you assume the speed of light is constant in a vacuum, that there is no change during transition, that every galaxy, every quasar, every star emits the same spectrum. You make that assumption, yeah, you're going to assume by the Doppler effect that the universe is expanding. Redshift can explain, however, other ways. There is a theory called tired light, and the particle model itself claims that the speed of light slows down as it moves through space. Making it possible that the universe is, both of these, making it possible the universe is a steady state universe and not expanding, even though we have evidence of a redshift of light. Well, the real main point of all this, dark energy in particular, is that energy is not real. Now, this statement is not because of the particle model. There's nothing about the particle model that demands that I say energy is not real. But a lot of good people finally understand energy is not real. So energy, just to go back to your physics book, is defined by scientists as the product of force times distance. Now, if nature is going to know about energy, and if it's real, nature is going to have to know how much force was used to move an object a certain distance. And it doesn't know either of those values. It doesn't know what the value of force is, or it doesn't know the distance it moved. But even if it did, nature doesn't know how to multiply. And so there's no way in nature you can ever find energy as being real. In fact, force is not real either. Momentum is not real. I've mentioned this many times before. But here's a test. Okay, if you want to go, let's analyze some energy. I'm going to ask you to take a container, go anywhere you want, and fill it with energy. Bring it to the lab to analyze it. The problem is you won't find any energy. You could, for example, put gasoline in a container, but that's gas or gasoline. It's not energy. It isn't. We don't see the effect of energy until we use gas in a combustion engine, for example. Well, mainstream physics uses energy as the magic pill. Dark energy causes the expansion of the universe. In the candle and the light bulb, energy makes a photon. In nuclear fission, energy heats the water. And then we also all go back to the E equals mc squared equation, and can energy make mass, convert it to mass? Actually, physicists say that's not the intent of that equation, but they use energy many times to explain things that I have talked about, and there are other reasons that you can explain how the light bulb generates light, how nuclear fission heats water. So they use energy to expand the universe. Here's the Big Bang. It was expanding but slowing down, and all of a sudden, magically, it's going faster. It's the magic. They used a magic pill here. This is a figure I use to show how when an atom is hit, the electron jumps up. When it falls down, it releases energy and makes a photon. Use it again. And here's one I did on fission. Neutron hits the U-235 atom, splits, and they say this energy heats the water. I say no, it's the moving neutrons that are released that hit the water, cause the water molecules to vibrate and heat up. But energy, even though it's not real, it is useful. It's a concept that we use to compare things. For example, it helps us select the best appliance, the best light bulb. We get the most light for the least amount of energy. We get the most cooling efficiency in a refrigerator with one that uses the least amount of energy. And the electric company, they like energy. They send you an electric bill based on your use of energy. But they don't send energy, they send G1 particles, and I explained that while talking about the hydroelectric dam. They send G1 particles, not energy. So sorry, the energy they charge for is not real. Sorry, the bill's real, you got to pay that. I'm sorry, or you're in trouble. So in conclusion, the particle model suggests that dark matter and energy, both of them, are not needed. The concept of shielding in the particle model eliminates the need for dark matter. The particle model claims that energy is not real and therefore cannot explain what causes the universe to expand at an accelerating rate. Further, the universe may not be expanding because G2 drag provides an alternate explanation for redshift, which I described in the video, Redshift and Tired Light. My name is Bob D. Hilster, and I am your particle model guru. Tune in next time when I'll explain more of the universe using the particle model. Thank you for your attention.